Alright guys, we're over here on lesson 10.5, area and non-rigid transformations. I want us to start out by doing what we normally do: scan the lesson, list 2 headings you would make to use an outline of this lesson. You can do that on your own. Then in our active vocabulary, I want you to define similar polygons in your own words. Go ahead and look back at lesson 7-2. You can find that in your textbook. In your table of contents, go to chapter 7, lesson 2. Then we're going to look at what we're talking about, some vocabulary from lessons 9.1 and 10.3. So here we're talking about segment of a circle, sector of a circle, and inscribed. Those are the 3 words that we're looking at. Segment of a circle, down here is, we're talking specifically about a part of the interior circle bound by a chord and an arc. Okay, it's part of the interior circle that's bound by a chord and an arc. So visually, if we're looking at a circle, okay, sort of a circle, oval thing, alright? A segment of a circle would be like if you just made a chord right there. This would be considered the segment of the circle, just the piece of it. Then, as we keep going, if we're talking about sector of a circle, you guys remember a slice of pie or a slice of pizza would be an example of a sector of a circle. So you guys, you'll remember again, if we're looking at a circle and it's talking about like a central angle here, it would be like a slice. That would be the sector of a circle. Then, lastly, we've got a figure or shape enclosed by another geometric shape figure is inscribed. So this right here means it's inscribed whenever it's enclosed by another geometric shape or figure. That would be inscribed. So again, if this circle were inscribed, we would call it like that. If it were inscribed or inside another shape, or if there were a circle and there happened to be a square that was inside that circle, it would be inscribed in the circle. Alright, last part here is where we're really going to focus in on this lesson, where we're talking about similar. Vocabulary link. Similar is a word used in everyday English. Find the definition of similar using a dictionary. Explain how its English definition can help you understand its meaning in mathematics. So we've talked about similarity before. We've had an extensive discussion on similarity, but this might help round out the discussion as we kind of come to an area of similarity and area. So that's what we're talking about today, area and similarity, essentially. So we'll talk about area of similar figures and dimensional changes. That's kind of our big ideas here. We'll go over some of this on the second page. I want you to do all of this. I've got it filled out here for you, and we'll walk through it a little bit. So, for the pair of similar triangles below, find the area of triangle DEF. DEF. Okay, we're going to walk through this, and we'll walk through it again a little bit as we look over our example in the lesson. But triangle DEF, okay, we're going to try to find that area. Well, how do we do that? It tells us over here, I've highlighted in green, that says the area for the smaller triangle, ABC, is 3. And it tells us that right here, you got 6 and 9 over here. So, it tells us that they're similar. That's a big part. So, since it's similar, we know that we can do some comparison, right? We might remember from similarity where we would say, oh, this angle and this side, and you know, if these 2 angles are similar to each other, then these 2 sides must be similar in the same ratio. Maybe we remember, maybe we don't. But we're kind of doing that same sort of thing where we say, okay, if these 2 triangles are similar and I'm going from ABC to DEF, then I could say the larger, what we're going to, can be on the numerator. So kind of what we're going towards goes in the numerator. So that 9 that we know. And where we're coming from goes in the denominator. So that would be in 6. So what we're going towards in the numerator, where we're coming from in the denominator. And that may be something that you'd like to write down in your notes. 9 being on the top and 6 being on the bottom, that gives us our ratio to work with. So what we actually do is we reduce that to lowest terms, which if we divide 9 by 3, we get 3, and we divide 6 by 3, we get 2. So our ratio of the areas is actually the square of that ratio. So once we bring it down to simplest terms, when we square that, we get our ratio of areas. There's that common proportionality whenever you square it. So whenever we square our answer 3 over 2, we get 9 over 4. Because 3 times 3 is 9 and 2 times 2 is 4. That's the ratio that we use. That's our conversion factor. That's our scale factor between these two triangles. At least their area anyways. So we would say if the scale factor is 9 over 4 for the area, well, we just multiply 9 over 4 times the area of the first triangle, the smaller one, to get the area of the second triangle, the larger one. So we do 9 over 4 times 3, which when we multiply that, we get 27 over 4. And when we convert that, we can say 6 3/4 or 6.75. That would be our area. If you did this with your calculator, you may get immediately the decimal. If you do it kind of in your head or on paper, you might stick with the fraction. And 27 over 4 is a correct answer, but typically it'll just be easier to use if it's in a mixed number or like a decimal number, 6.75. Okay. Then we'll go through dimensional changes. Really, these are just finding the scale factor. So we want some practice in finding the scale factor. Okay, if we know the areas of two similar geometric shapes, you can use them to find the scale factor between them. Well, it tells us here, area is 20 for the smaller, 45 for the larger. And we can say, all right, if we're going from the smaller, or from the larger to the smaller, right? So going from right to left, we would say, okay, I've got my smaller one where I'm going, right, on the top, and my larger one where I'm coming from on the bottom. That is equal to k squared. That's kind of our formula. We didn't talk much about that up here, but this is pretty much our formula where we would say, okay, going from one to the other, the areas are proportionally equal to the scale factor squared. Okay, the scale factor squared. That's why it's k squared. So we come down here and we say, alright, if I've got 20 over 45, which is, again, scale factor of the smaller is the numerator, scale factor of the larger is the denominator here. And we say, alright, 20 over 45, well, let's simplify that. So if we simplify it, we would have 4 over 9, and we get 4 over 9. When we square root that, because we're trying to get to k equals, you see that, just k, not k squared. When we square root that, we get 2 over 3. So our scale factor is actually 2 over 3 when going from the larger to the smaller. Okay, and going from the larger to the smaller would be 2/3, and that makes sense. It kind of seems like, oh, okay, this shape right here is about 2/3 the size of this shape right here. So that kind of makes sense. Now at the bottom, Anthony thinks that similar figures are equal figures. How can you explain to him that similar and equal are not the same? Okay, I don't want to read any writings of beat him with a stick or anything like that. Just try to explain it in your words to him. Now let's look at this kind of quickly. This is what we're looking at here. So in this example of these two triangles, the area of JKL is 40, and we're going to find the area of PQR. So we want to find the scale factor. So since we're going from the smaller on the left to the larger, where we're going to is on the top, where we're coming from is on the bottom. Going to on the top, coming from on the bottom. We reduce that to 6/5. And remember, the ratio of the areas is the square of 6/5. So we do 6/5 squared. When we do that, we end up with 36/25. And we can see that this is kind of like in a proportion. Okay, we could show it as a proportion. The area of the first triangle, PQR, the one that we're going towards, over the area of the one that we come from. So it's kind of that same ratio. We know that it's going to be exactly the same as the square of their sides. Okay, that scale factor of their sides. And so we got to 36/25. And then they do a little bit of math and multiply by 40 on both sides. That eliminates this 40 down here and puts it over here. And they end up with 57.6 when they multiply that out. So 40 times 36 divided by 25. And they get 57.6. Okay. That is really just as simple as this is. It's just a little bit of multiplying, dividing, remembering these steps, what to do. So let's look at a couple of these, and I'll show you just how easy it can actually be. So they break it down really a lot right here, so you can go back and reference that. But we're trying to find the area of the shaded figure, okay? And we're going to use, since they're similar, that's what it says, similar figures, we're going to use that information to find the area. So we're going from the unshaded to the shaded one. So from this one to this one. Now, if we look at this, we put where we're going to over the top, so 15, over where we're coming from, which is 5. So when we do that and we reduce it, we get the number 3. And in order to use that, we've got to use our scale factoring. Remember, it's the square, so remember it's k squared. We talked about that over here on this page. Our scale factor is actually k squared. Remember, we mentioned that right here, k squared. So once we find that ratio, we square it because we have to square it when we're trying to find the area, that area ratio. Realize how, this is squared, so that kind of does factor in. So when we do 3 squared, we get 9. And then we multiply our scale factor of 9 times this right here, 12. That was our original area. So 9 times 12 gives us the area of our new figure of 108. 108. Now let's look at this one over here. Kind of the same situation. So I've got right here 6/2. 6/2, and since I've got 6/2 because I'm going from smaller to larger, I've got 6 right here where I'm going towards, and where I'm coming from right here on the bottom. So 6/2. When I do 6/2, I get 3 again. So pretty easy. Again, remember, we then square that answer, because we have to square to find the area, and we get that scale factor of 9 shows up again. And then we multiply this by 20. Why did we multiply by 20? Because we go from this to this. We're trying to get to our answer over here of 180. We've got to go from our smaller to our larger, and that's kind of where we're going. We multiply that scale factor so that we can determine, okay, our answer needs to be 180. So if it's 180, that does make sense, right? I mean, you can see it's a pretty big change. The area on the left is 20, so the area of 180 on that right one seems pretty reasonable. Alright, now we get into something a little bit different, and we're almost done with what we're learning in this lesson. So, we look here, if we're looking at this page, the last one, it says 32, last one of learning, and then you've got your own work on the last page, last page. We've got scale factors and missing measures and similar figures. You can use the areas of similar figures to find the scale factor between them or a missing measure. So, just like in that second example on the example page where we were finding the scale factor, we're going to do that, and then we're going to use the scale factor to find x, that missing piece of the puzzle. So, first we find the scale factor. So if we let k be the scale factor between these two, okay, and again, we're trying to find x, so we know we're going from the left to the right, this larger one to the smaller one. So we would say, well, actually, in this one, we can find the scale factor either way, but we're going to go from the smaller to the larger. That's why, again, you've got this where we're going to over where we're coming from, and we say, all right, it's the area, so the area of where we're going to is 64, and the area of where we're coming from is 49. And that's squared, so then we do the square root, because it's k squared, remember. So we do the square root of that, and we get 8 over 7. When we have 8 over 7, okay, we can use that scale factor to then figure out a little bit right here. So that's our scale factor. We go from this right here, A, B, C, D, to F, G, J, H. So we do the same thing. If we're saying, okay, I've got C, D, so that's in A, B, C, D, and then I've got H, J. So I would do my known 10 over x. 10 over x equals my scale factor of 8 over 7. That's what we got right here. So when we do that, we do a little bit of substitution and multiplication. So we multiply both sides by 7 over 8x. Pretty much just switch it all around. You could work this out a little bit differently. You could say, I'm going to do cross multiplication. That's always okay. Multiply by, you would have 8x and equals 70, and then divide both sides by 8, and you'd get that same answer of x equals 8.75. Or you could do kind of like they did, where they just kind of sped it up and multiplied both sides by the reciprocal and x to get x by itself. I kind of like this one right here where we cross multiply. I feel like it makes a little bit more sense, and that's what I did myself. So, running a little bit short on time here, but we're going to just have you look at these. You can kind of see exactly what we do. That we've got 1 and 3 here. We go from our given. We're going from the unshaded to the shaded. So, we're going to 216. We come from 54, so it's 216 over 54 equals k squared. We do the square root of both sides, so you can see that right here in this step, square root of both sides, and we get k equals 14.7 over 7.3. We take that and we put it over equal to x over 8 equals 14 over 7.3. We end up with x equals 6.1. 16.1. Kind of the same scenario here, but we're going actually from our unshaded to our shaded, so from the larger to the smaller in this one. So we put where we're going to over where we're coming from. Sorry, I mixed up those colors. So where we're going to over where we're coming from. And you can see here that we get 300, the square root of 300 over the square root of 900, and that equals out to 17.3 over 30. We then put that in a proportion. 7.3 over 30 is equal to x over 21. Since that's in a proportion, we can cross multiply, which is what I did. We end up with 363.3 equals 30x. We divide both sides by 30 to get x by itself and get 12.11, which makes sense. You know, if you look at these two, this is 21, so it does make sense that this would be smaller, or right around 12 for our answer. Okay, makes common sense. Alright, this last page, you guys can do all of these except for the very last one I've blocked out there, that word problem. They're going to be worth 5 points each. So 5 points each. You guys got this. You can do it. I believe in you.